All right. Where do we leave off here? Oops. Let's see. Changing signal dispositions. All right. So let's get through this one. Unix system provide two ways of changing the disposition of a signal: signal system call and sig action system call. The signal system call, which is described in this section, was the original API for setting the disposition of a signal, and it provides a simpler interface than sig action. On the other hand, sig action provides functionality that is not available with signal. Furthermore, there are variations in this behavior of signal across Unix implementations, which mean that it should never be used for establishing signal handlers in portable programs. Because of these portability issues, sig action is the strongly preferred API for establishing a signal handler. After we explain the use of sig action in section 2013, we'll always employ that call when establishing signal handlers in our example programs. Although documented in section 2 of the Linux manual pages, signal is actually implemented in glibc as a library function later on top of sig action. Oh, okay. I guess they moved it out. Kind of a vestigial thing. Yeah, we can verify that just saying like man syscalls, look for signal. And there is a signal syscall though. So you can call it as a syscall. And then sig action. Oops. Yeah. Sig action. Bam. And there's RT sig action. So signal.h, you have a function pointer. Is that what that is? Why is it that weird syntax? Oh, because you pass it a handler. Wonder why it's let's do man to signal. Huh. Yeah, I mean this is the way I would expect it to be documented. You have the signal number, and you pass it a signal handler. Signal handler is in this type def of a void integer. So it's a bit of weird syntax having these parentheses here. And the return value here is a signal handler t, sig handler t. Oh, it's actually the return value as well. Interesting. Okay, so it does return a void, a function pointer. I guess that's the right C syntax for that. I don't like the way that looks. I like the type def version of it. So let's try to understand this. So whenever we have a function pointer, the name of the variable is next to the asterisk and wrapped in parentheses. So it's a void star is the return value. The name is handler. It's a very bizarre syntax. But void star is the return function, name is the handler, and then int is the argument tuple. So that whole thing is a function pointer, if you can believe it. Yeah, and so if you just like X this whole thing out, then we would have a very similar thing here. But why is this parentheses not here? It's also, oh, because, wait a minute. Yeah, why is there an int here? Is that right? I mean, it's not what I'm saying here. You know what? In times like this, we'll just talk to AI. Hey, explain this C syntax to me. Declarations are read inside out, starting from the identifier. So we're at signal here. Let's just scroll down here so you can see it there. Step by step, bring the function itself, signal, int sig void. Yeah, this all makes sense to me here. So everything from here to here makes sense to me. This part's, I mean, it's odd function pointer syntax, but yeah, signal is a function. It takes int sig as a signal number and a function pointer to a function that returns a void star and has an integer argument, or it returns void and has an integer argument. Sorry. Now look at the parentheses around this. So it returns nothing, but then has this int over here. Wait a minute. Huh? Now we look at the parentheses around star signal. That means that signal returns a pointer. Pointer to what? Look at what comes after. A pointer to integer. That means the pointer returned by signal points to a function. That function takes an integer, yeah. What does the function return? The very front void. It's that spiral, C-type spiral thing. It's so horrible. But it all goes. Signal is a function that takes an int signal number and a pointer to a function taking an int and returning void, and it returns a pointer to a function that takes an int and returns void. I mean, I can kind of get that out of reading this. It's just so freaking ugly. All right, and it's not the way that they defined it here, because this thing is a sig handler T. Yeah, it's not. Yeah, okay, well, we know it returns a function pointer that takes an integer, which is the handler itself, which is basically what this is saying up here. All right, continue reading. The function prototype signal requires some decoding. The first argument, sig, identifies the signal whose disposition we wish to change. The second argument, handler, is the address of the function that should be called when the signal is delivered. This information returns nothing, which is void, and takes one integer argument. Thus, the signal handler has the following general form. Yeah, okay. We described the purpose of the sig argument to the handler function in section 20.4. The return value of signal is the previous description of the signal. Like the handler argument is a pointer to a function returning nothing and taking one integer argument. In other words, we could write code such as the following to temporarily establish a handler for a signal and then reset the disposition of the signal to whatever was previously. So we declare old handler to be a function pointer to a function that takes an integer and returns void. We then call sigint with a new handler, getting it. Okay, so the return value is the old handler. If old handler is equal to sig error, then we exit. Then if signal sig int old handler is equal to, okay, So we just replace it. It's not possible to use signal to retrieve the current disposition of a signal without at the same time changing that disposition. To do that, we must use sig action. I get the feeling I'm gonna like sig action a lot better, which is like the struct version of it. We can make the prototype for signal much more comprehensible if using the following type definition for a pointer to a signal handler function. So we type def void star signal handler int. Yeah, that looks a lot better. If the GNU source feature test macro is defined, then glibc exposes a non-standard sig handler t data type in the sig handler header file. Instead of specifying the address of a function as the handler argument of signal, we can specify one of the following values: sig dfl, reset the disposition of the signal to its default. This is used for undoing the effect of earlier called signal that changed the disposition for the signal. Sig ign, ignore the signal. If the signal is generated for this process, the kernel silently discards it. The process never even knows that the signal occurred. A successful call to signal returns the previous disposition of the signal, which may be the address of the previous installed handler function or one of the constants. Sig dfl and sig ign. On error, signal returns the value sig error. I'm curious what these values are because they're basically pointers, right? So if we just do like a main test, let's see here, include signal.h, and then we'll do main here, and we got to include, this is going to be standard lib, and we might as well do standard IO while we're at it. And then in here, we have to say something like signal is going to take in, what's an example here? Is there an example? Signal, we'll just do like sig kill, and then this will be something like sig ignore. Oops. Sig ignore, if I can type. And we don't care about the return value. If we go over here, yeah, these are like, the error is a -1, the default is 0, and then ignore is 1. But these are like function pointers that have those sentinel values. I guess the rationale there is that there would never be a function pointer that is, I guess, signal handler. Wait a minute. How can you have a negative function pointer? That doesn't make sense. There's never going to be a negative memory address. Okay. How can a function pointer in C have a negative value like -1 assigned to it? Not an integer, so what is that? But in practice, people do it for a few reasons. In the compiler runtime, that's nice. Open often lets it happen because of how pointers and integers are represented in C. C allows casting between integers and pointers. You can legally cast an integer to a function pointer. This is syntactically valid in C, but it's undefined behavior to call it. Yeah, give you like a 2's complement, right? Or maybe it'll be -1 might be, what do you call it? Integer underflow, underrun or whatever. But not a real function. Let's print out the values of these. So if I do like, okay, just ignore that. We'll do printf, and we'll do %x. %x, oops, write that on a string, and new line, and semicolon, and this will be sig, sig error first, and then we'll say error, and then this will be default, which I think is DFL. So we'll say DFL here, IGN, and then we don't need, yeah, we need all that, okay. So make, build, test, yeah. So it's 1 byte, 2 byte, 16, 24, 32. So it's a 32. You would think it'd be a 64 because I have 64-bit. Like pointers is 64-bit, right? Maybe we should use pointers here. Oops, go away. Test.c. Okay. There's like a pointer thing here, right? Can I use that? Make test. There we go. So here we get the full 64-bit value. 1, 2, 3, 4, 5, 6, 7, 8 bytes. Yep. So I guess hex is like assuming a 32-bit value. Okay. Print sentinel pointers. Let's see. Make, oops. Make clean, make, build, print sentinel pointers. Okay, cool. I mean, it's just my lack of experience with C is why I had to like investigate that, because it seems rather odd to have like a signal handler be a return value, but then you also cram in these sentinel values to communicate errors and other states and stuff. So like it just seems kind of weird. A successful call to signal returns. Yeah, okay. Introduction to signal handlers. A signal handler, also called a signal catcher, is a function that is called when a specified signal is delivered to a process. We describe the fundamentals of signal handlers in this section and then go into details in chapter 21. Invocation of a signal handler may interrupt the main program flow at any time. The kernel calls the handler on the process's behalf, and when the handler returns, execution of the program resumes at the point where the handler interrupted it. The sequence is illustrated in figure 20.1. So you got delivery of the signal from the kernel, start of the main program, flow of execution, instruction M is hit, we get interrupted by the signal, kernel then says, hey, you're not going to be running this instruction anymore, I'm going to make you run the signal handler. So kernel calls signal handler on behalf of the process. It also does some like setup of the stack that we read about earlier in the man page. So there's some type of like stack stuff that it puts on a stack. It gets the thing set up to call the handler, and then it calls the handler, and then code of the handler is executed, it's returned, all the stuff that's on the stack gets popped back off, the program resumes at the point it was interrupted at, and then eventually you hit an exit, or you run forever, who knows. signal delivery and handler execution. Although signal handlers can do virtually anything, they should, in general, be designed to be as simple as possible. We expand on this point in section 21.1. Okay, installing a handler for SIGINT. So we got include, signal H, TLD, all that. We got a signal handler, just takes a signal, prints a thing that says ouch, returns a void, it's declared as static. Again, I don't know why. I think that static means that it's not available as a symbol for other. It's not in the symbol table, and it can't be used by other programs. Something like that when it's linking. So it doesn't collide with potentially things that are defined in other object files. I think that's what that means. I don't know though. Okay. We call a signal. We say, hey, on SIGINT, you run the SIG handler. And then forever, we're just going to print out and sleep 3 seconds. Cool. Listing 21 on page 399. 20-1 on page 399 shows a simple example of a signal handler and the main program that established it as a handler for the SIGINT signal. The terminating driver generates this signal. When we type the terminal interrupt character, usually it's Control-C, the handler simply prints a message and returns. The main program continuously loops. On each iteration, the program increments a counter whose value it prints. And then the program sleeps for a few seconds. To sleep in this manner, we use the sleep function, which suspends execution of its caller for a specified number of seconds. We describe this function in section 23.4.1. When we run the program on listing 21, we see the following. Ouch. Main program in the loop displays successive integers. We hit Control-C, it goes ouch. Yep. Makes sense. When the kernel invokes a handler, it passes the number of the signal that caused the invocation as an integer argument to the handler. This is a signal argument in the handler listing 21. If a signal handler catches only one type of signal, then this argument is of little use. We can, however, establish the same handler to catch different types of signals and use this argument to determine which signal caused the handler to be invoked. This is illustrated in listing 20.2, a program that establishes the same handler for SIGINT and SIGQUIT. SIGQUIT is generated by the terminal driver when we type the terminal quit character, usually Control \. The code of the handler distinguishes the two signals by examining the SIG argument and takes different actions for each signal. In the main function, we use pause, described in section 20.14, to block the process until a signal is caught. The following shell session log describes the use of this program. Int quit. Type Control-C, we caught SIGINT, 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 SIGQUIT. And listing 20-1 and listing 20- oops, why is my monitor? I got something wrong with my HDMI connection, I think. So my monitor just wants to die occasionally. I think it's a connection to the monitor itself because the video capture doesn't die. Well, hopefully that fixes it. I'm going to turn this light on. Move this guy around a little bit. Bam. Okay, and listing 20-1 and listing 20-2, we use printf to display the message from the signal handler. For reasons that we discussed in section 21-1.2, real-world applications should generally never call standard I/O functions from within a signal handler. However, in various example programs, we'll nevertheless call printf from a signal handler as simple means to seeing when the handler is called. Why is that? Because when you call printf, you're doing syscalls. Does printf have some type of like statically allocated memory or something? Curious why he says that. We can ask AI. Wonderful world of AI. Why is it that you should not call printf from within a signal handler in Unix? Printf is not async signal safe. That means that if signal interrupts the program while it's already inside printf or any other non-safe function, and the handler calls printf again, the internal state of the C library can become inconsistent. This can lead to deadlocks, corrupt state, or crashes. What async signal safe means: a function is async signal safe if it can be safely called from inside a signal handler without causing undefined behavior, even if the signal interrupts another call to that function. The POSIX standard defines a list of functions that are async signal safe function is not on that list. Why printf is unsafe? Printf is unsafe because it uses internal shared state. Exactly. Printf uses shared global structures like standard out buffers. If a signal interrupts printf mid operation and the handler calls printf again, the internal buffers can be corrupted. May allocate memory. Printf can call memory allocation routines, e.g. for formatting strings. Memory allocation is not async signal safe because you got to free it. It can call other unsafe functions. Printf internally calls functions like malloc, write, etc., which may not be safe in signal context. Example, what can go wrong? Suppose the main program is in the middle of printf hello so-and-so. Then signal arrives, interrupted, handler calls. Signal received. Now printf calls. Now two printf calls are competing to modify the same internal buffer, which can lead to exactly what we described. What you can do safely, use write instead. Write is async signal safe, so it's safe to use signal handlers. Write is a syscall to the standard out file number. So you can do the syscalls, you just can't use the buffered IO standard library stuff. Set a flag instead. Common pattern is to set the flag, and then have some thread handle the IO. Let's see. Does that mean that a printf is also not thread safe? Is thread safe? In most modern Unix systems, printf is thread safe in the sense that it won't crash or corrupt internal state when called concurrently from multiple threads. Why printf is thread safe? Most C libraries protect printf internally using mutexes. So if two threads call printf at the same time, one thread will block until the other finishes. The output won't interleave in a way that corrupts internal buffers. But output can still be mixed up, even though it's thread safe internally, the output can be interleaved. Why printf is not signal safe. Signals are not threads, and signal handlers can interrupt anywhere, even in the middle of a printf call. So thread safety using mutexes. Signal safety requires no unsafe operations at all. I'm trying to think through why signal safety is a higher level than thread safety. Why that might be. So if you had something where you go into the function, it acquires a lock, does its operations, release the lock when it's done. The entire thing is a critical section. then of course it's going to be thread safe because all the threads are competing for that lock. Well, if one of the threads acquires the lock, it's doing its business, there's some invalid state, it gets interrupted by a signal. Now that signal goes to acquire the lock. It won't be able to acquire the lock, it'll get a deadlock. That's why it's not signal safe. It's not that it's thread safety allows for the thread that acquired the original thread that acquired the mutex to make some form of progress. Whereas with a signal handler, it could be interrupting the thing that acquired the lock to begin with. And so it will immediately deadlock because it can't acquire the lock, and it's blocking the thing that acquired the lock from making any progress and ultimately release the lock. So, I mean, just my kind of like trivial example that I came up with here, that would be a reason why signal safety, or what they call async signal safe? Is that what they call it? Yeah, async signal safe is like a higher level of safety than thread safety. If a signal interrupts a printf call and the handler calling printf can corrupt shared state because the mutex might already be locked. Partially written. Is it the case that calling printf from a signal handler might deadlock the process because the thread that was interrupted holds the lock open and the handler is blocked from making progress, which blocked from getting the lock. Typical libc implementation, printf uses a mutex lock to protect internal file buffer. When a thread calls printf, it locks the mutex, writes the data, then unlocks. Thread A calls printf, it locks standard out mutex. The signal arrives while printf is still running. The still handler executes on the same thread. The handler calls printf again. Now the handler tries to lock the same mutex, but it already held by thread A. The interrupted call deadlock happens because the handler is blocking while looking for the lock that can never be released, since the original printf is paused inside the handler. Exactly. Why this is worse than thread deadlock. In threads, if thread A waits for a lock to be held by thread B can still run and release it. Yeah. In signals, the interrupted thread cannot continue until the handler returns. So the lock will never be released. The process is deadlocked forever. This is exactly why printf is not async signal safe. Even if it is thread safe, it is not safe to call from a single handler because the handler might try to re-enter a lock that is already held by the interrupted context. The handler could also call other non-safe functions internally. Save alternatives to write, set a flag. Okay, I got it. Okay. Sending signals with kill. One process can send a signal to another process using kill system call, which is analog to the kill shell command. The term kill was chosen because the default action of most signals that were available on early Unix implementation was to terminate the process. Okay. Got kill, PID, and a signal. Returns an error result as an integer. The PID argument identifies one or more processes to which the signal specified by SIG is to be sent. 4 different cases determine how PID is interpreted. If PID is greater than 0, the signal is sent to the process whose process ID is specified by PID. If PID equals 0, the signal is sent to every process in the same process group as the calling process, including the calling process itself. Sus v3 states that the signal should be sent to all processes in the same process group, excluding the unspecified set of system processes. It adds the same qualification to each of the remaining cases. If PID is less, so this is some of the process group stuff is something that I need to like learn more about, because I've experienced it in previous jobs. And I just don't fully understand all the mechanics behind how signals are sent to like members of the process group. If PID is less than -1, the signal is sent to all of the processes in the process group. So if PID is less than -1, the signal is sent to all processes in the process group whose ID equals absolute value of the PID. Okay. So you can say, here's my PID, negate it, and send it to that. That'll send to all the processes of the process group whose ID is equal to the absolute value of that. Sending a signal to all the processes in the process group finds particular use in shell job control. If PID is -1, the signal is sent to every process for which the calling process has permission to send a signal, except a init, process ID 1, in the calling process. If a privileged process makes this call, then all processes on the system will be signaled, except for these last 2. For obvious reasons, signals sent in this way are sometimes called broadcast signals. SUSV3 doesn't require that a calling process be excluded from receiving the signal. Linux follows the BSD semantics in this regard. If no process matches the specified PID, kill fails and sets error node to eSearch. No such process. eSearch. Okay. A process needs appropriate permissions to be able to send a signal to another process. The permission rules are as follows. A privileged cap-kill process may send signals to any process. The init process PID1, which runs with user and group of root, is a special case. It can be sent only signals for which it has a handler installed. This prevents the system administrator from accidentally killing a init, which is fundamental in the operation of the system. An unprivileged process can send a signal to another process if the real or effective user ID of the sending process matches the real user ID or saved set user ID of the receiving process, as shown in figure 22. This rule allows users to send signals to set user ID programs that they have started regardless of the current settings of the target process's effective user ID. Furthermore, on Linux and older systems that provide the set res UID system call, a set user ID program can take advantage of this rule to prevent itself being sent signals by the user that owns the executable. By using set res UID to make its saved set user ID the same as the real user ID, SUSV3 mandates the rule shown in figure 22. But Linux followed slightly different rules in kernel version before 2.0, as described in the kill man page. The SIG continue signal is treated specially. An unprivileged process may send this signal to any other process in the same session, regardless of the user ID checks. This rule allows job control shells to restart stop jobs process groups, even if the process of the job have changed their user IDs, i.e. they are privileged processes that have used the system call described in section 9.7 to change their credentials. Sending process. I have a real, effective, and safe set UID and a file system user ID as well, but it doesn't apply here. And then I can send to real or save set, and no one can set to effective. Interesting. Indicates that if IDs match, then the sender has permission to send a signal to the receiver. Permission is required for an unprivileged process to send a signal. Okay. Why is it that I can send signals to processes? Huh. Okay, that's good to know. If a process doesn't have permission to send a signal to the requested PID, then kill fails sending error node to EPERM, where PID specifies a set of the processes. PID is a set of processes. When PID is negative, kill succeeds if at least one of them could be signaled. We demonstrate the use of kill in listing 23. Don't really care about that. Checking for existence of a process is where you send kill to PID 0. The kill system call can serve another purpose. If a sig argument is specified as 0, the so-called null signal, then the signal itself is 0. I thought the PID was 0. Instead, kill. Oh no, sorry, I was confused. The null signal. So when you send the signal 0 to a process, it basically says whether it exists or not. So if I say something like echo $, so that's my PID for the shell, I can say kill -0, and then do echo. I can just do $, here. Boop. Echo that, and then if I do so. And then if I do something like, so those are the two errors you can get out. Like you don't have permission, or that it's not no such process. Sorry, that's the one I was looking for. So when you do kill 0 on yourself, because you obviously exist, you then get back no at exit code on the command. Cool. Okay. Instead, kill merely performs error checking to see if the process can be signaled. Read another way, this means we can use the null signal to test if a process with a specified process ID exists. If sending a null signal fails with the error eSearch, then we know the process doesn't exist. If the call fails with the error ePerm, meaning the process exists but we don't have permission to send a signal to it, or succeeds, meaning we have permission to send to a signal to the process, then we know that the process exists. Verifying the existence of a particular process ID doesn't guarantee that a particular program is still running, because the kernel recycles process IDs as processes are born and die. The same process ID may, over time, refer to different processes. Furthermore, a particular process ID may exist but be a zombie, i.e. a process that has died but whose parent has not yet performed a wait to obtain its termination status, as described in section 26.2. Various other techniques can also be used to check whether a particular process is running, including the following: the wait system call. Techniques can be used whether a particular process is running, including the following: the wait system calls. These calls are described in chapter 26. They can be employed only if a monitor process is a child of the caller. So monitor process is a child of the caller. You can wait on your... you wait your children, obviously. Semaphores and exclusive file locks. If the process that is being monitored continuously holds a semaphore or file lock, then we acquire a semaphore or lock. We know the process is terminated. We describe semaphores in chapter... So this requires that the process is actually a child of you. Semaphore requires code in the process that you're targeting. Let's see what the other ones are. IPC and the proc PID, I guess, would be the preferred way to go, right? IPC channels such as pipes and FIFOs, we set up the monitoring process so that it holds a file descriptor open for writing on the channel as long as it is alive. Meanwhile, monitoring process holds open a read descriptor for the channel, and it knows that the monitor process is terminated when the right end of the channel is closed because it sees end of file. The monitoring program can determine this either by reading from its file descriptor or by monitoring descriptor using one of the techniques described in chapter 63. The proc PID interface, for example, if a process with a process ID 12345 exists, then a directory proc12345 exists, and we could check using a call such as stat. Makes sense. I'm a big fan of proc, but proc does not always exist on Linux environments. If you're running in containerized environment, it's not always mounted inside your container, so you're not always guaranteed to be able to do that. All these techniques, except for the last, are unaffected by recycling of process IDs. Listing 23 demonstrates the use of kill. This program takes two command line arguments, a process ID and a signal number, and uses kill to send the signal to the specified process. If signal 0 is null, the null signal specified, then the program reports on the existence of the target process. Other ways of sending signals be raise and kill PG. I haven't used those before. Sometimes it's useful for a process to send signals to itself. We see an example of this in section 34.7.3. The raise function performs this task. Includes signal H. We do a raise a signal. So raise a signal, you would then go to the signal handler, probably in the same thread of execution. I did want to test that. While we're here, I did want to do my to-do, which is under pause resume. This didn't I have a to-do in here? I thought I had a to-do. Did I delete the to-do? Aww. That's in the library code. Okay. Well, let me see if I can remember what I did type out a to-do in here. I guess I didn't save it. Let me quit out of this. Quit out of this. Here we go. It's this thing here. Quit. Right quit. You know what I should do? I should jump to chapter 20. Get status. Make clean, obviously. Vim clang d. Change this to be 20. Just doing some cleanup here before I get this stuff added to the index, because I don't want to accidentally add something to the index that I forget to fix up. So that looks good to me. So I do get at all, get status, and then here I'm going to do my right quit. And then I'll do get status here, get diff. I should just be adding the to do. Okay, that's good. Okay, so now I can get out of here, and I'll clear here and go back over here, open this up again, jump to 20. Okay, so I'm gonna open up my print set. Oh, not that one. Pause. Okay, so mask USR1 for the main thread and signal to the main thread to see if one of the other thread handles it. So I forget how we do masking. Have we gotten there yet? Maybe that's why I haven't. You can change the disposition with the signal. We've seen that. But masking, I don't think it gets to masking until, yeah, sig proc max. Mask. Okay. So before we get there, I'm going to open up ChatGPT here and say, I want to mask the signal of USR, excuse me, of USR1, sig USR1 for the main thread, but not for the two threads I have already spawned. Give me code to do that. Okay. Huh? So we create a signal set, and then we say make it empty, so it's like zero initializing it basically. And then we say, hey, add to the set sig user 1, and then we're gonna do our sig mask. We're gonna say, hey, block this whole set, and there is no old mask. And if it's not, then we return exit failure. Cool. Make build pause resume. Let me do make clean first, and then make and build pause. I know it probably would have been built, but just want to make sure. So if I open up a new terminal and I send this to the main, will it get broadcast, or will it get handled by one of the threads? Oops. Would help if I actually copied it. Handler invoked, unpause thread, yep. Yep. So what that tells me that, which is what the book was saying, or I don't know if this book or the man page. Let's say mask is our one. Handles it and gets unpaused. Cool. All right. Let's go ahead and kill this. So what it says, like, even though you send the kill signal to the main thread, if the main thread has that mask, the kernel is going to send it to one of the threads, one of the other threads in that process, if you're sending it to the main thread. Now, if you send it to another, let's do pause resume, and say we do this code also in here, we'll just say exit failure. So we do it in the threads as well, but we don't do it in the main. Okay. Make build pause. Okay. So if we have that, and so now we can send the signal to the main thread like that. And say, okay, the main thread's happy, but we can't send signals to here. Oh, it is handler invoked. Interesting. Oh, what we're doing is invoking the handler on the main thread again. Yeah. So this thing blocks this from ever getting, so it never unlocks. But we get down here and we say, hey, we're going to pause the main thread. Main thread is unpaused, and then we are blocked on this stuff. But that just means that the main is available to handle the threads. So I'm going to delete this stuff now. I'm going to say, okay, indeed it does. Additionally, if you send a signal to a thread that has it masked, the main thread can also handle it. Also be interrupted. Handle it if it isn't masked. Come on. I hate that. Okay. Looks good to me. Well, I guess we can do this as well. There we go. Cool. Make it. Build it. Kill it. Wait a minute. So let's do this thread. Yeah, makes sense. All right, clear that. Sorry, just wanted to play around with that. All right, where are we at here? Other ways of sending signals, raise. We talked about the raise call there. Oops. What happened to my marker? I need something to fidget with. Well, I got extra ones in the closet here. Need something to fidget with, or else I can't read. All right. In a single-threaded program, a call to raise is equivalent to following a kill, get PID, sig. On systems that support threads, raise signal is implemented as pthread kill, pthread self, sig. We describe the pthread kill function in section 3.3.2.3, but for now it's sufficient to say that this implementation means that the signal will be delivered to the specific thread called raise. By contrast, the call kill get PID sends a signal to the calling process, and that signal may be delivered to any thread in the process. The raise function originates from C89. The C standard doesn't cover operating system details such as process IDs, but raise can be specified within the C standard because it doesn't require reference to process IDs. Okay, that makes sense. When a process sends itself a signal using raise or kill, the signal is delivered immediately, i.e. before raise returns to the caller. Note that raise returns a non-zero value, not necessarily -1, on error. The only error that can occur with raise is E invalid, because sig was invalid. Therefore, where we specify one of the sig constants, we don't check the return status of this function. Okay, good. The kill PG function sends a signal to all the members of the process group. Okay. So you got to get the PID of the process group. Calling kill process group is equivalent to the following call to kill, which is, kill negative process group. Yep. A process group is specified as 0. Then the signal is sent to all processes in the same process group as the caller. Susv3 leaves this point unspecified, but most Unix implementations interpret this case in the same way as Linux. Displaying signal descriptions. Each signal has an associated printable description. These descriptions are listed in the array syssig list, For example, we can refer to sys-sig list, sig pipe, to get the description for sig pipe, broken pipe. However, rather than using the sys-sig list array directly, the stir signal function is preferable. So you can just say, hey, I got the signal, what is it? I'm going to call stir signal. Do you have to do the extern thing? Const char. Okay. The stir signal function performs bounds checking on the sig argument. The stir signal function performs bound checking on the sig argument and then returns a pointer to a printable description of the signal or a pointer to an error string if the signal number was invalid. On some other Unix implementations, stir signal returns null if sig is invalid. Aside from bounds checking, another advantage of stir signal over the direct use of sys-sig list is that stir signal is locale sensitive, so that signal descriptions will be displayed in a local language. An example of the use of stir signal is shown in listing 24. The p-signal function displays on standard error the string given in its argument message, followed by a colon, and then the signal description corresponding to sig, like stir signal, p-signal is locale sensitive. The p-signal, stir signal, and sys-sig list are not standardized part of SUSV3. They are nevertheless available in many Unix implementations. SUSV4 adds specifications for p-signal and stir signal. Signal sets. Many signal-related system calls need to be able to represent a group of different signals. For example, sig action and sig proc mask allow a program to specify a group of signals that are to be blocked by a process, while sig pending returns a group of signals that are currently pending for the process. We describe these syscalls shortly. Multiple signals are represented using a data structure called a signal set, provided by the system data type sigset t. SUSV3 specifies a range of functions for manipulating signal sets, and we now describe these functions. On Linux, as on most, on the next page here. On Linux, as in most Unix implementations, the sigset t data type is built as a bit mask. However, SUSV3 doesn't require this. A signal set could conceivably be represented using some other kind of structure. SUSV3 requires only that the type of sigset t be assignable. Thus, it must be implemented using either some scalar type, e.g. an integer, or a C structure, perhaps containing an array of integers. The sig empty set function initializes a signal set to contain no members. That's why there's 32 signals in the standard set, because then you have 32 bits available to represent every signal in a signal set. And now that we have 64, if you want to use the same structure, to represent the set, then you'll have to be limited by 64 signals. Okay. One of sig empty set or sig fill set must be used to initialize a signal set. This is because C doesn't initialize automatic variables, and the initialization of static variables to 0 can't portably be relied upon as indicating an empty signal set, since signal sets may be implemented using a structure other than bit masks. For example, for the same reason, it is incorrect to use memset to zero the contents of a signal set in order to mark it as empty. Another initialization, individual signals can be added to a set using sig_add set and removed using sig_del set. For both sig_add set and sig_del set, the sig argument is a signal number. The sig is member function is used to test for membership of the set. The sig is member function returns 1 true if sig is a member of set, or 0 false if it is not a member, or -1 on error, e.g. sig is not a valid signal number. All right, the GNU C library implements 3 non-standard functions that perform tasks that are complementary to the standard signal set functions just described. sig_and set, sig_or set, sig is empty set. These functions perform the following tasks. sig_and set places the intersection of sets left and right into the destination. sig_or set places the union of sets left and right into the destination. And sig_empty set returns true if set contains no signals. Example program. Using the function described in the section, we can write the functions shown in listing 24, which we employ in various later programs. The first of these, print sig set, displays the signals that are members of the specified signal set. This function uses the nsig constant, which is defined in signal.h, to be 1 greater than the highest signal number. We use nsig as the upper bound in a loop that tests all signal numbers for membership. Let me read this. The first of these, print sig set, displays the signals that are members of the specified signal set. This function uses nsig constant, which is defined to be 1 greater than the highest signal number. We use nsig as upper bound in a loop that tests all signal numbers for membership of a set. Although nsig is not specified in SUSV3, it is defined on most Unix implementations. However, it may be necessary to use implementation-specific compiler options to make this visible. For example, on Linux, we must define one of the feature test match macros. The print sig mask and print pending sig functions employ print sig set to display respectively the process signal mask and the set of currently pending signals. The print sig mask and print pending sigs functions use sig's proc mask and sig's pending system calls respectively. We describe sig proc mask and sig pending system calls in section 2010 and 2011. So this thing just print sig set, print sig's mask, yeah. These are just helper functions. All right. Signal mask, blocking signal delivery. Okay, how many pages we got left here? Okay, not a lot. We're getting through it. It's only 6 p.m. Got a couple hours here. For each process, the kernel maintains a signal mask, a set of signals whose delivery to the process is currently blocked. If a signal that is blocked is sent to a process, delivery of that signal is delayed until it's unblocked by being removed from the process signal mask, or it could go to any thread. That's not that process. In section 33.2.1, we'll see that signal mask is actually a per thread attribute, and that each thread, I've already explored that. Multi-thread process can independently examine and modify its signal mask using the pthread sigmask function. I didn't use that, did I? I think I had AI do that for me. Yeah, I did do that. Pthread sigmask. Okay. A signal may be added to the signal mask in the following ways. When a signal handler is invoked, the signal that causes the invocation can be automatically added to the signal mask. Whether or not this occurs depends on the flags used when the handler was established using SIG action. When a signal handler is established with SIG action, it's possible to specify an additional set of signals that are to be blocked when the handler is invoked. The SIG proc mask system call can be used at any time to explicitly add signals to and remove signals from the signal mask. We delay discussion of the first two cases until we examine SIG action and discuss SIG proc mask now. So this thing, you say, hey, int how const SIG set, and then you give the old set. How is like block, unblock, or set the mask, and then you give it the thing. We can use SIG proc max to change the process signal mask to retrieve the existing mask or both. The how argument determines the change that SIG proc mask makes to the signal mask. SIG block, the signal specified in the signal set pointed to by set are added to the signal mask. In other words, the signal mask is set to the union of its current value in set. SIG unblock, the signals in the signal set pointed to by set are removed from the signal mask. Unblocking a signal that is not currently blocked doesn't cause an error to be returned. SIG set mask, the signal set pointed to by set is assigned to the signal mask. In each of the case, if old set argument is not null, it points to a SIG set T buffer that is used to return the previous signal mask. If we want to retrieve the signal mask without changing it, then we specify null for the set argument, in which case the how argument is ignored. To temporarily prevent delivery of a signal, we can use the series of calls shown in listing 25 to block the signal and then unblock it by resetting the signal mask to its previous state. So temporary blocking delivery of a signal. Oops, wrong page. Oop. So this code, we say I'm going to declare a SIG set T called block set and one called previous mask. Then there's a comment that says initialize a signal set to contain SIG int. So first we have to zero initialize it. So we say SIG empty set, and then we say SIG at set, and we give it the block set with the SIG int. And then block SIG int, save previous signal mask. So then we say SIG proc max block, here's the block set, and then write the previous mask to the previous location. And then we can restore it with with SIG proc max SIG set mask, give it the previous mask, give it null. Makes sense. SusV3 specifies that if any pending signals are unblocked by the call to SIG proc max, then at least one of those signals will be delivered before the call returns. So when you call this thing, you unblock the mask, it's gonna process the signal before this thing even returns. In other words, if we unblock a pending signal, it is delivered to the process immediately. Attempts to block SIG kill and SIG stop are silently ignored because you can't block either of those. If we attempt to block these signals, SIG proc mask neither honors the request nor generates an error. This means that we can use the following code to block all signals except SIG kill and SIG stop. We say SIG fill set, block set. Makes sense. Pending signals. If a process receives a signal that is currently blocking, that signal is added to the process set of pending signals. When and if the signal is later unblocked, it is then delivered to the process. To determine which signals are pending for a process, we can call SIG pending. The SIG pending system call returns the set of signals that are pending for the calling process in the SIG set T structure pointed to by set. We can then examine set using its SIG is member function described in section 29. If we change the disposition of a pending signal, then when the signal is later unblocked, it is handled according to a new disposition. Wait a minute, let me reread this. We can then examine set using we can then examine set using the sig is member function described in section 20.9. If we change the disposition of a pending signal, then when the signal is later unblocked, it is handled according to the new disposition. Although not often used, one application of this technique is to prevent the delivery of a pending signal by setting its disposition to sig ignore or to sig default if the default action for the signal is ignore. As a result, the signal is removed from the process set of pending signals and thus not delivered. Signals are not queued. Yeah, I already know that. Okay. Spend 1, 2, 3, 4 pages on telling me signals aren't queued. And then changing signal dispositions, a sig action, and then waiting for signal to pause. Yep. This is all stuff that I'm very familiar with now. The set of pending signals is only a mask. It indicates whether or not a signal has occurred, but not how many times it has occurred. In other words, if the same signal is generated multiple times while it's blocked, then it is recorded in the set of pending signals and later delivered just once. One of the differences between standard and real-time signals is that real-time signals are queued, as discussed in section 22.8. Listing 26 and listing 27 show two programs that can be used to observe that signals are not queued. The program in listing 26 takes up to 4 command line arguments as follows: sig sender pid number sig number and sig num2. The first argument is the process ID of the process we want the program should send the signal. The second argument specifies the number of signals to be sent to the target process. The third argument specifies the number of signals that should be sent to the signal number that is to be sent to the target process. If a signal number is supplied as a fourth argument, then the program sends one instance of that signal after sending the signal specified by the previous arguments. In the example of the shell session below, we use a final argument to send signal to the target process. The purpose of sending the signal will become clear in a moment. Okay. The program showing list 27 is designed to catch and report statistics on signals sent to the program. In listing 26, the program performs the following steps. The program sets up signal handler to catch all signals. It isn't possible to catch sig kill or sig stop, but we ignore the error that occurs when trying to establish a handler for these signals. For most types of signals, the handler simply counts the signal using an array. If SIGINT is received, the handler sets a flag .SIGINT that causes the program to exit its main loop, the while loop described below. We explain the use of the volatile qualifier and the sig atomic T data type used to declare the .SIGINT variable. Makes sense. Yeah, because you might be reading halfway through. It's a race. We might be reading, and while you're reading non-atomically, the signal handler writes to it, and then you get like a torn read. Okay, let's read the program here just to make sure we understand this one. So we got integer num6, the signal, and j. I think this one's pretty straightforward. I don't know if we need to read it. It just sends stuff. Okay. If a command line argument was supplied to the program, then the program blocks all signals for the number of seconds specified by that argument, and then prior to unblocking the signals, displays a set of pending signals. This allows us to send signals to the process before it commences the following step. The program executes a while loop that consumes CPU time until .SIGINT is set. So it's a spin loop, or what do you call it, spin lock? Spin loop, hot loop. It's spinning. um, After exiting the while loop, the program displays counts of all signals received. We first use the two programs to illustrate that a blocked signal is delivered only once, no matter how many times it is generated. We do this by specifying a sleep interval for the SIG receiver and sending all signals before the sleep interval completes. So we say SIG receiver 15, throw it in the background, gives you a PID and sleeps for 15 seconds. We then take that PID and we call the sender. Say I want you to send, let's see, that's 1, 2, 3, 4, 5, 6. That's a million SIG 10, which is SIG USR 1. Send a million of those, and at the end, send SIG 2, which is SIG int. Sending 10 to process so-and-so a million times, exiting, and then the receiver says, hey, pending signals are an interrupt and a single signal 10. And then it removes the mask, and signal 10 is caught one time, and then the receiver exits because it got the flag set. The command line argument to the sending program specified in SIG USR 1 and SIG int signals, which are signals 10 and 2 respectively on Linux x86. From the output above, we can see that even though 1 million signals were sent, only one was delivered to the receiver. Even if a process doesn't block signals, it may receive fewer signals than are sent to it. This can happen if the signals are sent so fast that they arrive before receiving process had a chance to be scheduled for execution by the kernel, with the result that the multiple signals are recorded just once in the process pending signal set. If we execute the program listing 27 with no command line arguments, so that it doesn't block signals and sleep, we see the following: SIG receiver, and then we send a million without it waiting, and 10 got caught 52 times. Of the million signals sent, just 52 were caught by the receiving process. The precise number of signals caught will vary depending on the vagaries of decisions made by the kernel scheduling algorithm. The result for this is that each time the sending program is scheduled to run, it sends multiple signals to the receiver. However, only one of these signals is marked as pending and then delivered when the receiver has a chance to run. Oh, Jesus. Excuse me. All right. Catching and counting signals. This is the program that we just went over. Changing signal dispositions. SIG action. The SIG action system call is an alternative signal for setting the disposition of a signal. Although SIG action is somewhat more complex to use than signal, in return, it provides greater flexibility. In particular, SIG action allows us to receive the disposition of a signal without changing it, and to set various attributes controlling precisely what happens when a signal handler is invoked. Additionally, as we'll elaborate in section 22.7, SIG action is more portable than signal when establishing a signal handler. So we've got SIG action, we give it a signal, SIG action struct, and another SIG action struct. The SIG argument identifies a signal whose disposition we want to receive or change. This argument can be any signal except SIG kill or SIG stop. The ACT argument is a pointer to a structure specifying a new disposition for the signal. If we are interested only in finding the existing disposition of the signal, then we can specify null for this argument. The old ACT argument is a pointer to a structure of the same type and is used to return information about the signal's previous disposition. If we are not interested in this information, then we can specify null for this argument. The structures pointed to by ACT and old ACT are as follows: are of the following type. SIG action, there's a signal handler, a signal set, flags controlling the handler invocation, and then some memory for a SA restore, which is not to be used for application. The SIG action structure is actually somewhat more complex than shown here. We consider further details in section 21.4. The SA handler field corresponds to the handler argument given to signal. It specifies the handler of the signal of a signal handler or one of the constructs SIG ignore or SIG default. The SIG mask and SA flag fields, which we discuss in a moment, are interpreted only if SA handler is the address of a signal handler, that is, a value other than SIG ignore or SIG default. The remaining field, SA restorer, is not intended for use in applications and is not specified by SUS v3. The SA restorer field is used internally to ensure that on completion of a signal handler, a call is made to the special purpose SIG return system call that restores the process's execution context so that it can continue executing on the process at the point where it interrupted by the signal handler. An example of this usage can be found in glibc source file sysdeps unix sysv linux i386 SIG action. C. Boop. The SA mask field defines a set of signals that are to be blocked during invocation of the handler defined by the SA handler. When the signal handler is invoked, any signals in this set are not currently part of the set that are not currently part of the process signal mask are automatically added to the mask before this handler is called. These signals remain in the process signal mask until the signal handler returns, at which time they are automatically removed. The SA mask field allows us to specify a set of signals that are permitted to interrupt execution of this handler. In addition, the signal that caused the handler to be invoked is automatically added to the process signal mask. This means that a signal handler won't recursively interrupt itself if a second instance of the same signal arrives while the handler is executing. Because block signals are not queued, if any of these signals are repeatedly generated during the execution of the handler, they are later delivered only once. The SA flags field is a bit mask specifying various options controlling how the signal is handled. The following bits may be ORed together in this field. We got a bunch of stuff here. So SA, no cloud stop. If SIG is SIG child, don't generate the signal when a child process is stopped or resumed as a consequence of receiving a signal. SA, no child wait. If SIG is SIG child, don't transform children into zombies when they terminate. For further details. Oh God, 26. What is chapter 26? That is monitoring child processes. Okay. SA no defer. When this signal is caught, don't automatically add it to the process's signal mask while the handler is executing. The name SA no mask is provided as a historical synonym for SA no defer, but the latter name is preferable because it's standardized in SUS v3. SA on stack, invoke the handler for the signal using an alternative stack installed by SIG T stack. SIG alt stack, sorry. Recthend. When this signal is caught, reset its disposition to the default SIG default before invoking the handler. By default, the signal handler remains established until it is explicitly disestablished by further calling SIG action. The name SA one shot is provided as a historical synonym. Okay, the one shot, that makes sense. Reset hand. SA restart, automatic restart system calls interrupted by this signal handler. Automatic restart. C20. Okay, we'll cover that later. SIG info. Invoke the signal handler with additional arguments providing further information about the signal. And we'll handle that later. All of the above options are specified in SUSV 3. An example of using SIG action is shown in 21.1. Waiting for signal pause. Calling pause suspends execution of the process until the call is interrupted by a signal handler. Or until an unhandled signal terminates the process. When a signal is handled, pause is interrupted and always returns -1 with error node set to E enter. As example of use of pause is provided in listing 22 in sections so-and-so. We look at various other ways that a program can suspend execution while waiting for a signal. Summary. A signal is a notification that some kind of event has occurred. It may be set to a process by the kernel, by another process, or by itself. There is a range of standard signal types, each of which has a unique number and purpose. Signal delivery is typically asynchronous, meaning that the point at which the signal interrupts execution of the process is unpredictable. In some cases, e.g. hardware-generated signals are delivered synchronously, meaning that delivery occurs predictably and reproducibly at a certain point in the execution of a program. By default, a signal either is ignored, terminates the process, with or without a core dump, stops the running process, or restarts a stop process. The particular default action depends on the signal type. Alternatively, a program can use signal or SIG action to explicitly ignore a signal or establish a program-defined signal handler function that is invoked when the signal is delivered. For portability reasons, establishing a signal handler is best performed using SIG action. A process with suitable permissions can send a signal to another process using kill. Sending the null signal is a way of determining if a particular process ID is in use. Each process has a signal mask, which is a set of signals whose delivery is currently blocked. Signals can be added to and removed from the signal mask using SIG-proc mask. If a signal is received while it's blocked, then it remains pending until it is unblocked. Standard signals can't be queued, that is, a signal can be marked as pending and thus later delivered only once. A process can use the SIG pending syscall to retrieve a signal set, a data structure used to represent multiple different signals, identifying the signals that it has pending. The SIG action system call provides more control and flexibility than signal. Then setting the disposition of a signal. First, we can specify the set of additional signals to be blocked when a handler is invoked. In addition, various flags can be used to control the actions that occur when a signal handler is invoked. For example, there are flags that set the older unreliable signal semantics, not blocking the signal, causing invocation of the handler and having the disposition of the signal reset to its default before the handler is called. Using pause, a process can suspend execution until a signal arrives. Further information, so-and-so provide background implementation of signals in Linux, details of the implementation of signals in SysV Release 4, the GNU-C library manual contains an extensive description of signals. The GNU-C library manual. Let's do something like we just visit signal handling. So cool. All right. Exercises. As noted in section 23, SIG action is more portable in Signal for establishing a signal handler. Replace the use of signal by SIG action in the program. Nope, not doing that. Write a program that shows that when the disposition of a pending signal is changed to be SIG ignore, the program never sees catches a signal. Don't want to do that. Write a program that verifies the effect of a SA reset hand and SA no defer flags when establishes. Don't care about that. Implement the SIG interrupt function described in section 21.5 using SIG action. 21.5. Not doing any of those. I did a little bit for this project or for this chapter. I wrote 2 little programs I'm happy with. Let's go back here, make clean. And then Vim readme. Let's go ahead and mark this as done. And then 21, which is signals. Signal handlers. So like some things that I'm like interested in is less like the C APIs for all these things. It's more like I'm curious about how the kernel and the, well, I guess it's the kernel. I guess the compiler is involved in it too, but basically like how the kernel sets up the trampoline for the signal handler. Like assuming like an x86-64 ABI, like what is the actual steps that the kernel performs in user or in kernel space and in user space to like set up the stack and all the registers and everything so that the signal handler can execute, and how does it undo that stuff and then jump back to where it interrupted the program to begin with. Like all those details are things that are like super interesting to me, but I don't think we're going to scratch the surface of that stuff. There is a book that I have that I ordered that's on my coffee table right now that dives into more of that level of stuff that I'm curious about picking up. It's another massive book, and given how long it's taken me to get through this thing, like I'm nearing a third of the way through here. So given how long it's taken me to do this one, I'm like motivated by the amount of progress I've made so far, but I'm also a little bit like demotivated by the amount of time it's taken me. I mean, I started this around like maybe the week before New Year's, and I really only have been focused on it the past week, and I've made about a third of the way into it. I think I can get it done before February if I stay at this pace every day, getting like 1 or 2 sessions, or 2 solid sessions. Some days I can get a morning session, an afternoon, and an evening session. Like doing 3 sessions a day on some days, then I think I can make it through the entire book by the end of February or by the end of January, because it's only 17th right now. But that's like reading all of this in like 1 month, fully digesting it, doing the same thing for that book, because that book's of similar length. I think it might be a couple hundred pages less than this, but similar length book, even more in depth and technical stuff. Like a lot of this stuff I can cruise through because it's like not super in depth. It's in depth in some areas that are like not interesting to me, so I can cruise through those. And it also doesn't really go deep into some of these things. So deep as in like the layers of abstraction that it's defining. It kind of stops at like syscall boundary, C API boundary. Like that's kind of where this book stops. It doesn't really go any further down than that. And I want to get into like processor instructions. I want to get more into like how the compiler works, how the linker works. So I'm thinking like the next book that I pick up is going to be a lot shorter because I don't want to like have to grind through a textbook for like a month. So I'm thinking about reading KNRC. I read a good part of the beginning of the KNRC, maybe the first half, maybe not even that, when I was in college. And I had intended on finishing it. I just never did. And I've lost that copy of it. So I reordered that. So that's on my coffee table as well. So I'm thinking about doing KNRC next. And then from there, potentially picking up that book that I mentioned. Actually, let me go grab it real quick. So these are the books that are on my radar. This 2 books are CUDA by example. This is like a pretty old book at this point. I think it's like 2011 or something, maybe even earlier. I got maybe 26 pages into it, and then I paused execution on that one. But it's very small. It's a short book, maybe 300 pages total. Just kind of introduction to CUDA. And CUDA C and CUDA C++. And then this is the book that's more like the algorithms book, from what I understand, for heterogeneous, massively parallel computations. And so this is Programming Massively Parallel Processors, 4th edition, a hands-on approach. And this is another book that is in the same domain of like me wanting to get better at programming GPUs. So now I have a Blackwell GPU that I purchased when I bought these books with the sole intention of doing CUDA programming on it. However, I started using that GPU to do my OBS live streaming. And so while I could run CUDA programs on it, like if you reset the graphics card, it basically is going to take down my stream. So I think what I need to do before I take on this whole project is to either move to the onboard graphics for my streaming and do CPU processing, which is not a good option because I'm doing multi-streaming, or buy a new GPU, or just build like a dedicated streaming machine. I think I'm leaning towards that, but we'll see. But that's kind of like where I'm at with these 2. Those are 2 that are on my radar. I mentioned KNRC. Yeah, I mean it's pretty much kind of like table stakes for anyone who's doing C programming, I think. And then this is the book that I was talking about. This thick boy here. It is actually it's reasonably smaller than what I'm reading now. It's about 1,100 pages, so it's about 400 pages shorter than the Linux System Programming Interface. This is called Computer Systems: A Programmer's Perspective. And this is a textbook from what I understand, like a literal textbook. I think it's Carnegie Mellon was so Pearson's the publisher. I think it's Carnegie Mellon though that is the so the authors are all from Carnegie Mellon. So I think this either is or was a book that they used at Carnegie Mellon at some point for the curriculum. And it was just recommended online. And so I picked it up, and I've just been leafing through it, looking at the different diagrams, and I'm like, wow, this is like the secret sauce of computing. Like this is how computers actually work under the hood, like I've never found a good book that teaches like assembly or how to disassemble C programs and like understand what the disassembly is. This program, like just leafing through it, every other page, not every other page, but like it's the probability of you hitting a page that has a disassembly on it is very high. So yeah, I'm excited to dive into some of this just to get, like, I mean, just this page here has assembly on it, like. And I mean, it's a lot of theory too. It's not just all practical stuff. So, but I think that's the Q is KNRC, and then I'll make a decision at that point. So we're going to finish the Linux programmer interface. Then I'm going to take on KNRC, and then I'm going to make a decision on whether I want to do the computer systems, a programmer's perspective, or if I want to dive into GPU programming. Yeah. But yeah, I feel like these books, I got a good queue ahead of me. This is awesome. Like, I feel like I'm getting a full re-education in a lot of stuff that I just didn't learn fully and I haven't used a lot in my career. Stuff that I've been wanting to learn for ages and just haven't had the time. So I'm afforded the luxury of time now, so I might as well do all this stuff. All right. It is 6:30. We can make some progress on signal handlers section. Let's go ahead and get our commit done here. Git diff. So 20 is ticked, and then 21 signal handlers. Get the status. I'm gonna RM chapter 20, build zig, vim chapter 20. Make file. Actually, you know what? I'll just leave those in. Git checkout chapter 20. Or git restore 20. Build.zig. Git status. Okay, git CI. I want to say finish chapter 20. And we'll do git push. And we'll do TT7 done. So we are officially 31% complete with the book. Making progress, baby. All right. So let's get on signal handlers here. My goal for this chapter is to get something out of this I don't already know. So signal handlers are invoked when signals occur. The kernel or other processes can send signals, or the process can send a signal to itself. And the process can register signal handlers. Signal handler, so the disposition for the signal determines whether the signal is ignored, or whether it crashes the program, or whether it stops or resumes the program, or whether a signal handler is ran. And sig action is the main syscall for wiring up signal handlers. You can mask signal handlers temporarily to prevent their delivery, and then remove the mask. There's some signals that you can't ignore, you can't mask. Things like sig kill or sig stop. I think those are the two. But the rest of them are fair game. Trying to think what I might learn about signal handlers. The details of the trampoline I want to learn. I don't think I'll learn that from this chapter. There is the additional data that you can send in the signal that I'm not really familiar with. Other than the signal number. Trying to think what else. I guess more information about like when you're invoking a signal handler, what it can actually do safely, like what libc what libc APIs are async signal safe. What, like when you might want to allow for signal handlers to be interruptible by themselves, and what the implications of that might be. Preventing deadlocks, stuff like that. But yeah, we'll see what I end up learning from this chapter. This chapter continues the description of signals begun in the previous chapter. It focuses on signal handlers and extends the discussion as started in section 20.4. Among the topics we consider how to design a signal handler, which necessitates a discussion on reentrant and async signal safe functions. Okay, that's great. Alternatives to performing a normal return from a signal handler, in particular, the use of non-local goto for this purpose. That one I'm like, okay. This is where my C knowledge is not great. I know goto is kind of like a jump, but I don't know what a non-local goto is. That like a long jump type thing? I don't know. Handling of signals on an alternate stack. That is something I'm curious about. They kind of mentioned it a couple times in the previous chapter. So how do you set that up? Why you would want to do that? I want to learn about that. The use of sig action, SA sig info flag to allow signal handlers to obtain more detailed information about the signal that caused its invocation. That's what I mentioned before. How a blocking system call may be interrupted by a signal handler, and how the call can be restarted if desired. Oh, interesting. Yeah, this is all interesting stuff. Okay, let's do a page count here. So it's 422, and this goes all the way to 446. So that's 24 pages. It's 640, 740. I think maybe I'll go for another hour-ish. And then I'll probably log off just to wind down for the evening, get a good night's sleep. How long have I been going now? For an hour, 2 hours? Okay. All right, designing signal handlers. In general, it is preferable to write simple signal handlers. One important reason, I forgot to mention, my mind's scattered right now. This book has been easy to read because there is a PDF available on it on the internet. And I have the physical book. I like reading physical books, but not all the physical books I read are going to have PDFs regularly available. So I'm thinking about getting like a scanner. So as I'm reading, I can just scan the page real quick, have it pop up on screen, instead of like pointing the camera down at the book. I feel like I've tried that in the past and it just doesn't work. They do sell like page scanners on Amazon for like $70. So I don't know if they're good or not though. But getting one of those to work where I can just like do a scan, have it show up, read the page, do a scan, have it show up, read the page. I think that would be really, really cool. It'll prevent me from being able to seek to like other pages. But I guess if I seek to another page and I'm reading it, I could just scan that and that'll show up. So I don't know. That's something that I've been thinking about doing for future reading. All right. In general, it is preferable to write simple signal handlers. One important reason for this is to reduce risk of creating race conditions. Two common designs for signal handlers are the following. The signal handler sets a global flag and exits. The main program periodically checks this flag and, if it is set, takes appropriate action. If the main program, see, those have to be atomic though, because like if we look back to the code, I was supposed to read this code. Back here, they had on page, let me go back here. So this handler, when they get to SIGINT, they just assign into SIGINT, got SIGINT. But got SIGINT is declared as a volatile sig atomic T. And then assignment into it just makes it like, okay, an atomic assignment, I guess. And then when we read it, it's called got SIGINT T. We just read it like we would normally read it. So there's no fancy like functions. Like in Go, the atomics package, you have like atomic functions that you call and pass pointers and stuff. But this stuff, you just declare it as an atomic, and I guess the compiler knows to treat those reads and writes as atomic reads and writes without any special function calls or anything. All right, so let's go back to here. The main program periodically checks this flag, and if it's set, takes appropriate action. If the main program cannot perform such periodic checks because it needs to monitor one or more file descriptors to see if I/O is possible. If the main program cannot perform such periodic check because it needs to monitor one or more file descriptors to see if I/O is possible, then a signal handler can also write a single byte to a dedicated pipe whose read end is included among the file descriptors monitored by the main program. Interesting. We show an example of this technique in section 63. It seems like everything interesting is in chapter 63. The signal handler performs some type of cleanup and then either terminates the process or uses a non-local goto to unwind the stack and return control to a predetermined location in the main program. In the following sections, we explore these ideas as well as other concepts that are important in the design of signal handlers. Signals are not queued, revisited. Really? We need to revisit that? Okay. Section 2010, we noted that delivery of a signal is blocked during the execution of its handler unless we specify a SA no defer flag to SIG action. If the signal is again generated while the handler is executing, then it is marked as pending and later delivered when the handler returns. Okay. That's if it's blocked though. We also already noted that signals are not queued. If the signal is generated more than once while the handler is executing, then it is still marked as pending and it will later be delivered only once. That signal can disappear in this way. That signals can disappear in this way has implications for how we design signal handlers. To begin with, we can't reliably count on the number of times a signal is guaranteed. Furthermore, we may need to code our signal handlers to deal with the possibility that multiple events of the type corresponding to the signal have occurred. We'll see an example of this when we consider the use of SIG-child signal in section 26.3.1. Reentrant and async safe signal safe functions. Not all system calls, even system calls aren't safe. Interesting. That's something that I learned. Excuse me. Not all system calls and library functions can be safely called from a signal handler. To understand why requires an explanation of two concepts: reentrant functions and async signal safe functions. So reentrancy, when I first encountered it with locks, meant that if a thread acquires a lock and then tries to reacquire the same lock, it can re-enter into that lock and reacquire it, and it only prevents other threads from acquiring the lock. That is a sort of reentrant lock, reentrant mutex. Reentrancy with respect to glibc functions, I've learned recently in reading this book, is a concept where it's related but not the same, where a function, if it is reentrant safe, can be called either in a single signal handler or in multiple threads at the same time without interfering with each other. So if you start, or even the same thread. So if you call into a function, say like read or something, or write might be a better example. Or not write, printf. Printf would be a good example. So we call into printf in our main thread, and then, we need an example of a function that uses statically allocated memory, because basically statically allocated memory is one of the major issues that prevent reentrancy. Because if you have a library function that returns a pointer to statically allocated memory that has the result, and the caller doesn't copy that result into another buffer somewhere, the next time you call that function, it's going to reuse that buffer, that statically allocated memory. So if you have a call to that, you return a pointer, and then later you call into some other thing deep into the stack, and it calls the same function, it overwrites that shared static memory. Now your original pointer is affected, and when you pop back up the stack, now that original memory has been like invalidated. It's now garbage. So even a single thread that has no signal handler, just calling the same function twice, has issues where memory is being monkeyed with in ways that are not safe. So I would say like reentrancy is like a certain level of, like, reentrant safe functions give you a certain level of protection, but like the next level up would be async signal safe, which is where it's safe to call the function in a signal handler or in multiple threads. So I think it kind of goes reentrant safe, thread safe, async signal safe. Async signal safe is like, you can call this function from signal handlers, you can call it safely from multiple threads concurrently at the same time, and it's all good. Where you get tripped up with async signal safe is where, like, a good example would be anything that requires a mutex. Like, say you're in the main thread, you acquire a mutex, you start doing operations, the signal handler gets invoked, so you jump into signal, or the kernel puts you into the signal handler. Now it tries to acquire the same lock, and it's waiting on the thread that it interrupted to release that lock for it to be able to make progress. So it's a complete deadlock. So that would be an example of like an async signal safe, a non-async signal safe function. So that's kind of like my mental model for reentrancy and async signal safe and thread safe. Thread safety is just that you can call the thing from multiple threads at once, and they're not guaranteed to make progress in any particular amount of time, but over the period of the execution of the process, they eventually make progress. Nothing's guaranteed really with the kernel. It could just deschedule all your threads and never run them if it wants to. All right, so not all system calls and library functions can be safely called from a signal handler. To understand why requires an explanation of two concepts: reentrant functions and async signal safe functions. Reentrant and non-reentrant functions. To explain what a reentrant function is, we need to first distinguish between single-threaded and multi-threaded programs. Classic Unix programs have a single thread of execution. The CPU processes instructions for a single logical flow of execution through the program. In a multi-threaded program, there are multiple independent concurrent logical flows of execution within the same process. In Chapter 29, we'll see how to explicitly create programs that contain multiple threads of execution. However, the concept of multiple threads of execution is also relevant for programs that employ signal handlers. Because a signal handler may asynchronously interrupt the execution of a program at any point in time, the main program and the signal handler in effect form two independent, although not concurrent, threads of execution within the same process. A function is said to be reentrant if it can safely be simultaneously executed by multiple threads of execution in the same process. So reentrant is kind of like thread safety. In this context, safe means that the function achieves its expected result regardless of the state of the execution of any other thread of execution. Let's ask AI. I'm learning about the concept of reentrancy. What's it called? Reentrancy in libc and with respect to multi-threaded programs and even single-threaded programs with signal handlers. How does reentrant safe is that how you spell it? Entrant. This would be reentrancy. How does reentrant safe functions differ from what people would normally call thread safe functions? I think thread safety is not as good as reentrancy. That's my guess. Thread safe are often used interchangeable in casual discussion, but libc and POSIX, they mean different things with different guarantees. I'll walk from strict to relaxed guarantees and tie it back to signals in libc. Reentrancy, the strongest guarantee. A function is reentrant safe. It can be interrupted at any point and safely called again before the first call finishes without any corruption or deadlock. This includes interruption, a signal handler in the same thread, a recursive invocation, another thread without any coordination. Key properties of reentrant functions: uses no global static mutable state, has no heap allocation. Why does it have no heap? Oh, because of the freeing. You don't know when to free. No internal locks. Calls only other reentrant functions. Operates only on caller provided data. Uses only local stack variables. Why signals matter. Signals can interrupt any instruction. If a function holds a lock, is modifying global state, is inside malloc, is in the middle of standard I/O buffering, and a single handler calls the same function, undefined behavior. This is why POSIX defines async safe functions. They are a subset of reentrant functions. It's a subset of reentrant. Thread safe, a weaker guarantee. A function is thread safe if multiple threads can call it concurrently without causing data races or corruption. This is usually achieved by internal mutexes, thread local storage, atomic operations. Thread safe is not equal to reentrant. A thread safe function may not be reentrant. Why? It may lock a mutex. It may depend on thread safe, thread local state. It may allocate memory. It may temporarily modify shared structures. All of those are fatal in signal handlers. Thread safe uses lock, not reentrance. Concrete libc example. Okay, single threaded programs still care. Mental model to keep. Reentrant, can I safely interrupt this function and call it again immediately? Thread safe, can multiple threads call this at the same time if the scheduler cooperates? So would it be appropriate to say that thread safety is a weaker set of guarantees than reentrancy reent is still weaker than async signal safe. Thread safety is the weakest, safe for concurrent execution of multiple threads, assuming no asynchronous interruption. Allowed internally mutexes TLS, heap allocation, lazy initialization, standard IO buffering, pretty much everything. You just can't data race, and you got to be able to work with the other threads cooperatively. Reentrant, so it's safe to be interrupted and re-entered, including recursive calls. So no global static state, no locks, because if you acquire a lock and then you are interrupted, that's this async signal safe though. I guess why are locks and heap what do you mean by TLS consistency? And oops. And why are locks and heap not allowed for reentrancy? Give examples of where they might go wrong that don't involve signals. Async signal safe. Important subtlety worth knowing at your level, async signal safe is not just reentrant plus documented. Okay, that's good to know. POSIX requires no internal state, no locks, no interaction with non-atomic libc internals, well-defined behavior even if interrupted in the middle of any other libc call. Thread local storage. Shit, I thought it was TLS transport layer storage, transport layer security. Why locks break reentrancy? No signals involved. Self deadlock. Okay, so we create a mutex, and then it's a global mutex. Oh, because it has to be accessible for multiple threads, it has to be global, and therefore it's global state. What if the caller passes in the mutex? Gives it to another thread and passes it in. Because they're global state. What if the mutex was stack allocated? Would it be safe for reentrancy? What if you stack allocated a mutex, then passed it into a pointer to it to another thread that you spawn to coordinate access to a shared resource? You then pass that mutex pointer into a function, possibly reentrant function. Would that be reentrant safe? Since the memory is stack allocated and the other thread is eventually going to release the lock. Okay, so can the same function be entered again before a previous invocation finishes without relying on external progress? Okay, in this case, we rely on external progress. Once you share mutex between invocations, you've already violated that requirement, regardless of whether the mutex lives on a stack, heap, thread local storage, or .BSS. Where the mutex lives is irrelevant. Who can see it is what matters. Your proposed setup made explicit something like so we got F that locks and unlocks the thread. We got a caller, we stack allocate the mutex, we create a thread, and then we call F. And the worker is going to acquire the thread and release it as well. F might be re-entered recursively, called back, etc. The worker thread also uses M. The failure mode 1, blocking on external progress. If F is re-entered while mutex is held, eventually forbids this. The re-entrant function must not block waiting for another invocation to complete. Not depend on another thread running to make progress. Even if the other thread eventually unlocks, the inner invocation is now dependent on external scheduling. It violates the definition of reentrancy. Okay. That makes sense. Alright, let's continue reading the book. Let's continue from here. I know we were a little bit further along, but to explain what range function is, we first need to distinguish between single-threaded and multi-threaded programs. Classically, yeah, we already know that. Okay, we don't need to reread that. A function is said to be reentrant if it can safely be simultaneously executed by multiple threads of execution in the same process. I don't know about that. That's thread safety. That's not reentrancy. A function is said to be reentrant if it can safely be simultaneously executed by multiple threads of execution in the same process. I mean, a reentrant function does need to have that property, but it's not the only property. That's thread safety. In this context, safe means that the function achieves its expected result regardless of the state of execution of the other thread of execution. SUS-V3 definition of reentrant function is one whose effect when called by two or more threads is guaranteed to be as if the threads each executed the function one after the other in an undefined order, even if the actual execution is interleaved. A function may be non-reentrant if it updates global or static data structures. A function that employs only local variables is guaranteed to be reentrant. If two invocations of, i.e., two threads executing the function simultaneously attempt to update the same global variable or data structure, then these updates are likely to interfere with each other and produce incorrect results. For example, suppose that one thread of execution is in the middle of updating a linked list data structure and to add a new list item when another thread also attempts to update the same linked list. Since adding a new item to the list requires updating multiple pointers, if another thread interrupts these steps and updates the same pointers, chaos will result. Such possibilities are in fact rife within the standard C library. For example, we already noted in section 7.1.3 that malloc and free maintain a linked list of freed memory blocks available for reallocation from the heap. If a call to malloc in the main program is interrupted by a signal handler that also calls malloc, then this linked list can be corrupted. For this reason, the malloc family of functions and other library functions that use them are non-reentrant. Other library functions are non-reentrant because they return information using statically allocated memory. Examples of such functions described elsewhere in this book include crypt, get pwnam, get host by name, get served by name. If a signal handler also uses one of these functions, then it will overwrite information returned by any caller. returned by an earlier call to the same function from within the main. Hold on, I need to reread this. If a signal handler also uses one of these functions, then it will overwrite information returned by any earlier call to the same function from within the main program. Functions can also be non-reentrant if they use static data structures for their internal bookkeeping. The most obvious examples of such functions are members of the standard I/O library, printf, scanf, and so on, which update internal data structures for buffered I/O. Thus, when using printf from within a single handler, we may sometimes see strange output or even a program crash or data corruption if the handler interrupts the main program in the middle of executing a call to printf or another standard I/O function. Even if we're not using non-reentrant library functions, reentrancy issues can still be relevant. If a signal handler updates programmer-defined global structure that is also updated within the main program, then we may say that the signal handler is non-reentrant with respect to the main program. If a function is non-reentrant, then its manual page will normally provide an explicit or implicit indication of this fact. In particular, watch out for statements that the function uses or returns information in statically allocated variables. Example program. Listing 21.1 demonstrates the non-reentrant nature of the crypt function. As command line arguments, the program accepts two strings. The program performs the following steps, calling crypt to encrypt the string in the first command line argument and copy the string to a separate buffer using stirdup. Establish a handler for sigint generated by typing Control-C. The handler calls crypt to encrypt the string supplied in the second command line argument. Enter an infinite for loop that uses crypt to encrypt the string in the first command line argument and check that the return string is the same as that saved in step 1. In the absence of a single, the strings will always match in step 3. So call crypt to encrypt the string and copy it. Okay. Establish handler for sigint. Handler calls crypt to encrypt the string supplied in the second argument. Enter an infinite loop that uses crypt to encrypt the string in the first command line argument and check whether the return string is the same as. Okay. So basically, we're going to be doing an encryption in a signal handler that's going to interfere with the encryption in the main thread. So we repeatedly type Control-C to generate sigint, and we see mismatch call. Comparing the mismatch and handled values in the above output, we see that in the majority of the cases where signal handler is invoked, it overwrites the statically allocated buffer between the call to crypt and the string comparison in main. Okay. If CR1 is equal to null, set for a signal. So basically this crypt function, the thing that it returns must be statically allocated, or basically it must be using some type of memory that's shared between these calls. So I'm calling this. These arguments are not going to change. So it's the call itself and what it returns. This isn't going to change. This isn't going to change. This isn't going to change. Whatever this thing returns, the pointer to memory here, it's going to get overwritten by the signal at some point. So if the call is delivered when it's up here doing like a call num increment, like say it interrupts that, then I think it's safe. But as soon as it interrupts the crypt function itself, which is going to be the majority of the instructions, like you're not spending a lot of time doing string compare or incrementing counters or doing a branch here, like comparison to equal or comparison to not equal 0, like, or this condition. Oh no, there's an empty condition there. Like the bulk of the instructions are going to be in the crypt function. So chances are the signal is going to interrupt the execution of the crypt function itself. So that's probably why this is like so obvious. Anyways, standard async signal safe functions. An async signal safe function is one that the implementation guarantees to be safe when called from a signal handler. A function is async signal safe either because it is reentrant or because it is not interruptible by a signal handler. Table 12.1 lists the functions that various standards require to be async signal safe. In this table, the functions whose names are not followed by a v2 or v3 were specified as async signal safe in POSIX 1990. SUSV2 added the functions marked v2 to the list, and those marked v3 were added in SUSV3. Individual Unix implementations may make other functions async signal safe, but all standards conformant Unix implementations must ensure that at least these functions are async signal safe. If they are provided by the implementation, not all of these functions are provided on Linux. SUSV4 makes the following changes to table 21.1. The following functions are removed. The following functions are added. Okay. I mean, it's a big list. SUSV3 notes that all functions not listed in table 21.1 are considered to be unsafe with respect to signals, but points out that a function is unsafe only when invocations of the signal handler interrupts the execution of an unsafe function, and the handler itself also calls an unsafe function. In other words, when writing signal handlers, we have two choices. Ensure that the code of the signal handler itself is reentrant and that it calls only async signal safe functions, or block delivery of signals while ensure that the code of the signal handler itself is reentrant and that it calls only async signal safe functions. Block delivery of signals while executing code in the main program that calls unsafe functions or works with global data structures also updated by signal handlers. Say we're not taking the signals, so we can do signal unsafe stuff here. And then we're not doing signal unsafe stuff. We'll take the signals. That'll invoke the signal handler. Then it can put up its own blocks, and then it can do like not unsafe signal stuff. Because it's guaranteed to not. It's guaranteed by the main. Or by the normal program, the normal thread is guaranteed that it. Well, I guess it can only guarantee itself, not other threads, unless you put a lock around it. I'm trying to think that they're. So you put a lock around doing thread or async signal unsafe stuff, And then if the thread's unlocked, I think it's better to acquire the lock when you're guaranteeing that you can handle signals. That way all threads are blocked on that lock, and say everyone's okay with, like, you have to be only doing signal safe stuff now if you want this lock. And you can make it like a read write lock, so all the readers can read off of it and be like, I'm doing async signal safe stuff. And as soon as one of them wants to do something unsafe, async signal unsafe, they have to acquire the lock, and thus they're prevented from doing it. If the signal handler is running and it's doing unsafe stuff. I think that would work. This is very confusing. It's better just in signal handlers, just keep them simple and just don't do any async signal unsafe stuff inside your handlers. Just make it all async signal safe. And then outside your signal handlers, you can do whatever you want that's thread safe. That's like a lot easier mental model for me. I don't know why you would make it more complicated. The problem with the second approach is that in a complex program, it can be difficult to ensure that a signal handler will never interrupt the main program while it is calling an unsafe function. For this reason, the above rules are often simplified to the statement that we must not call unsafe functions from within a signal handler. Yeah. If we set up the same signal handler function to deal with several different signals, or use the SA no defer flag to sig action, then a handler may interrupt itself. As a consequence, the handler may be non-reentrant if it updates global or static variables, even if they are not used by the main program. Use of error no inside of signal handlers. Because they may update error no, the use of functions listed in table 21.1 can nevertheless render a signal handler non-reentrant. Yeah, this error no global, or it's a thread local, but the error no thread local variable is just like super sloppy, man. I guess it's a convenience in that, like, you can. I like the looking at the return value of the syscall and determining the error based on that, and not this like, oh, you got to check the thread local storage to actually make sure that there wasn't an error. It's just like, when you do that, now you have the problem that they're going to get into, which is like, in a single thread, you have a signal handler interrupting it, and now it's writing to error no. So the use of error no inside of signal handlers, because they may update error no, use of the functions listed in table 21.1 can nevertheless render a signal handler non-reentrant, since they may overwrite the error no value that was set by a function called from the main program. The workaround is to save the value of error no on entry into a signal handler that uses any of the functions in table 21.1 and restore error no value on exit from the handler, as in the following example. So, hey, I interrupted you. I'm going to save your error no, and then do my thing, and I'll assign it back, and then you'll be fine. Use of unsafe functions in example programs in this book. Although printf is not async signal safe, we use it in signal handlers in various example programs in this book. We do so because printf provides an easy and concise way to demonstrate that a signal handler has been called. Why not just use write? Is write's safe? And to display the contents of the relevant variables within the handler. For similar reasons, we occasionally use a few other unsafe functions in signal handlers, including other standard I/O functions and stir signal. Real-world applications. Sorry, let me go to this. Real-world applications should avoid calling non-async signal safe functions from signal handlers. To make this clear, each signal handler in the example program that uses one of these functions is marked with the comment indicating that the use is unsafe. global variables and sig atomic T data types in volatile. This is good stuff. I'm not going to make it to the end here. It's almost 7:30. I think I'll leave it there because this global variables and sig atomic T data type, super interesting. Actually, no, let's go ahead and get to other methods of terminating a signal handler, since that's like kind of like a more of a partition there. So let's finish this. Notwithstanding reentrancy issues, it can be useful to share global variables between the main program and the signal handler. This can be safe as long as the main program correctly handles the possibility that the signal handler may change the global variable at any time. For example, one common design is to make a signal handler's sole action the setting of a global flag. This flag is periodically checked by the main program, which then takes appropriate action in response to deliver the signal and clears the flag. When global variables are accessed in this way from a signal handler, we should always declare them using the volatile keyword. See section 6.8. Wait a minute, volatile keyword. In order to prevent the compiler from performing optimizations that result in the variable being stored in a register. All right, let's go back to 6.8. I don't remember that. Did they talk about volatile? Oh, that was for the long jump stuff. Is there an example program? Maybe they use volatile somewhere here? Or here it is, problems with optimizing compilers. Yeah, they use volatile there. I totally forgot about that. All right, so reading and writing global variables may involve more than one machine language instruction. And a signal handler may interrupt the main program in the middle of such an instruction sequence. We say that access to the variable is non-atomic. For this reason, the C language standard and SUSV3 specify an integer data type sig atomic T, for which reads and writes are guaranteed to be atomic. Thus, a global flag variable that has been shared between the main program and a signal handler should be declared as follows: volatile sig atomic T flag. We show an example of the use of sig atomic T data type in listing 22.5 on page 466. Note that the C increment, plus plus, and decrement operators don't fall within the guarantee provided for sig atomic T. On some hardware architectures, these, that's great. Oops, damn it. So plus plus and minus minus are not atomic on the sig atomic T type. On some architectures, these operations may not be atomic. All that we are guaranteed to be safely allowed to do with sig atomic T variables is set it within the signal handler and check it within the main program, or vice versa. So increment is not atomic because it can be a read, modify, write instead of a single atomic increment instruction. C99 and SUSV3 specify an implementation should define two constants, sig atomic min and sig atomic max, that define the range of values that may be assigned to variables of type sig atomic T. The standard requires that this range be at least negative 127 to 127. If sig atomic T is represented as a signed value, or 0 to 255 if it is represented as an unsigned value. On Linux, these two constants equate to the negative and positive limits for signed 32-bit integers. Okay, we'll leave it off there then. Just put my bookmark in there, move that over there. Boom. Cool. Good status, clear. So we're approaching 1/3. I would say we're about 1/3 at this point. So we're 428, and there is what? 1,400, I think. Total, not including the appendices. Yeah, 1,400. So BC. No, I don't have basic calculator. Python. If I do 1,400 divided by 3. 466. I'm not 1/3 done. I got about 40 pages still. Alright. We will hit 1/3 tomorrow though. And tomorrow I would like to get through all of the signal stuff. So that's the remainder of this chapter and the next chapter. And that will leave us, if we go back here. So right now we're at other methods of terminating. So we're here. And I didn't get very far today, to be honest. I just got this far. I didn't get very far today because I was playing around with some example code. And I also didn't get on until kind of late this afternoon. So tomorrow, what I want to do is get through all of this from here to here. And then potentially make progress into this signal advanced features. I don't think I'll be able to get through all the signal stuff, to be honest. Okay, I'll leave it there then. I'll be on tomorrow morning to resume on signal. Wait a minute. I did get all of it. I got from here all the way down to here. Other methods for terminating signals here. That's where I'm at. Okay. All right. That gives me a little more confidence that we can finish the remainder of this chapter and then do all of Signal's advanced features tomorrow. Okay. That's what I was thinking. I was thinking we can get through everything tomorrow. All right. Cool. I'll be on tomorrow to resume signal handlers and signal advanced features.